Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to the Power Electronics lecture series at ComSat Cyberabad. In this lecture, we shall discuss the step-up cycloconverter. Cycloconverter. A cycloconverter is a frequency changer that converts AC power at one input frequency to AC output power at different frequency. There are two types of cycloconverter. One is called step-down cycloconverter, in which the frequency of the output signal is less than the frequency of the input signal. The other type is called step-up cycloconverter, in which the frequency of the output signal is greater than the frequency of the input signal. So, how we can achieve a variable frequency or voltage at the output of a converter? There are two methods which are used to achieve variable frequency or voltage at the output of a converter. Method 1 is called DC link converter method, which is a two-stage conversion method. At stage 1 we are using the rectification, and stage 2 we are using the inversion. To achieve variable frequency or voltage at the output, we are using the control devices for both the conversions. The other method is called direct method, which is a single stage conversion method, in which we are using the controlled switches to achieve variable frequency or a voltage. To summarize the methods of achieving variable frequency and a voltage at the output of a converter, that we can achieve it with a DC link method or without a DC link method, which is a single stage conversion method, which is furtherly classified into single phase cycloconverter and a three-phase cycloconverter. In this lecture, our focus will be on the single phase step-up cycloconverter. DC link converter method. As we discussed earlier, the DC link converter method has two conversion stages. One is called rectification and other is called inversion. To control both the DC link voltage and the output voltage of a three-phase inverter, we are using the control devices at both the rectification and at the inversion stages. So there are few advantages and disadvantages of the DC link method. Advantages are the output frequency can be varied from 0 to the related value by the turn off time of the device nowadays, which is quite low by the invention of fast switching devices. The control circuitry is very simple as compared to the single stage conversion method. It has a high input factor, so as the power factor depends on the alpha when we are using the controlled rectifier. It is good for high frequency applications. The disadvantages are due to the two-stage conversion method, which makes the converter circuit bulky and less efficient. Forced commutation required at the inverter stage in case of thyristors are used. As we are getting the staircase waveform from the inverter, which makes the overall converter circuit unstable at low frequencies. So the other method used for achieving variable frequency and voltage at the output of the converter is called direct method. By using this method, we will investigate the single phase to single phase cycle converter by using midpoint and a break type, and also three phase to single phase cycle converter, and also three phase to three phase cycle converter in the preceding sections. So single phase to single phase step up cycle converter by using midpoint method. Figure 6a shows the midpoint configuration of the single phase to single phase cycle converter. Here our objective is to achieve an output voltage of a larger frequency than the source frequency. In this figure, the frequency of the output signal is 6 times the frequency of the input signal. So for achieving larger frequency than the source frequency signal, let's see the operation of this circuit, how it will works. So for the positive half cycle of the input signal, we have polarity positive and negative like this. So the thyristor T1 and T4 belongs to the positive group, means these thyristors will work for the positive half cycle of the input supply, and T2 and T3 belongs to the negative group, means these thyristors will work for the negative half cycle of the input supply. Here for the positive half cycle of the input supply, we have polarity like this, positive and negative. The point A is more positive with respect to point K and B, and K is more positive with respect to B only. So at omega t equal to 0, thyristor T1 is triggered, and thyristor T1 is triggered, and we are getting this path of load current, and we can easily compute the output voltage, which is equal to this one, which is the part of the voltage VAK. So at omega t equal to theta 1, T1 is force commutated and T4 is triggered. So at omega t equal to theta 1, T1 is turned off by force commutation and T4 is triggered. So as we discussed earlier, point K is more positive with respect to point B, so the load current flows like this, which is the opposite to the polarity marked, or the current direction is shown in the circuit, and we are getting the output voltage like this for the thyristor for conduction. So at omega t equal to theta 2, again T4 is force commutated. At omega t equal to theta 2, T4 is force commutated, and thyristor T1 is triggered, and again the current will flow like this, and we are getting the output voltage like this. So again at omega t equal to theta 3, thyristor T1 is force commutated, and we triggered thyristor T4, and again the load current will flow like this. We are getting the output voltage like this, and so on up to the omega t equal to pi. At omega t equal to pi, the thyristor T4 is line commutated. Why? The polarity at the input side is now changing like this. It's negative and positive. And now after omega t equal to pi, the thyristors are SCRs T2 and T3. T2 and T3 are in the conduction mode. We need the gate pulses to turn on these SCRs. So again, for this polarity, positive and negative, we know that the point B is more positive with respect to point K and A, and K is more positive with respect to A only. So at omega t equal to pi, we trigger the thyristor T2, and the current will start flowing through the load like this, and we are getting the output voltage of this. And at omega t equal to pi plus theta 1, T2 is force commutated, and we triggered thyristor T3 and the current will start flowing like this, and we are getting the same polarity of the input voltage at the output, which is the negative, which means we are getting the VAK envelope portion at the output. So at this is the point pi plus theta 2. Again at pi plus theta 2 we are triggering thyristor T2 and T3 is force commutated, and we are getting this output voltage. And at point pi plus theta 3 we are triggering thyristor T3 and T2 is force commutated, we are getting output voltage like this. And again at point pi plus theta 4 we are triggering the thyristor T2 and force commutated the thyristor T3, and we are getting this output voltage. And at point pi plus theta 5 we are triggering the thyristor T3 and force commutated the thyristor T1, and we are getting this output voltage up to omega t equal to 2 pi. And from here the next cycle of the input supply starts, and it will follow the same procedure as we discussed here. So in this manner we are achieving an output voltage of a signal having frequency 6 times of the source frequency, or having the time period 1/6 of the input signal time period. So we can clearly see that if we divide the input signal into 6 equal portion, this is the one cycle, this is the 2, this is 3, this is 4, this is 5, and this is 6. So we are achieving the output voltage signal having frequency 6 times of the source frequency, or the time period 1/6 of the input signal. In this slide we shall discuss the single phase to single phase step up cycloconverter with bridge type topology. Figure 7a shows the circuit diagram of single phase to single phase cycloconverter with bridge type topology. Here our objective is to achieve an output voltage of a frequency larger than the source frequency. So in this figure the SCRs from T1 to T4 belongs to the positive group, and the SCRs from S1 to S4 belongs to the negative group. Let's see how this circuit will work for achieving an output voltage of a frequency larger than the source frequency. So for the positive half cycle of the input signal, we have polarity at the input side like this. The point A is positive and the point B is negative. Point A is positive and the point B is negative. So at omega t equal to 0, the SCRs T1 and T2 are triggered, and these are starting conducting, and the current through the load will follow this path and it goes back to the load, and we have the output voltage like this. And at omega t equal to theta 1, the SCRs S1 and S2 are triggered, and the SCRs T1 and T2 are force commutated. So at omega t equal to theta 2, the current through the S1 through the load and goes to the S2 and back to the source. So this is the path for the load current, and we are getting the output voltage like this. and omega t equal to theta 2, we are again triggering the thyristors are SCRs T1 and T2, and we are force commutating the SCRs S1 and S2, and we are getting this output voltage. And again, this the load current will follow this path. And again, at omega t equal to theta 3, the SCRs S1 and S2 are triggered, and we are getting output voltage like this, and the load current will be again like this, and so on up to the omega t equal to pi. Both the SCRs T1 and T2 and S1 and S2 turn on and off alternatively up to omega t equal to pi. In other words, we can say that from omega t equal to 0 to pi, the SCRs from the positive group T1 and T2 and the SCRs from the negative group S1 and S2 are active to achieving the output voltage. So at omega t equal to pi, the S1 and S2 are the last conducting SCRs. So at omega t equal to pi, these SCRs are line commutated, and we triggered the SCRs T3 and T4. And the polarity at the input side reverses itself. So now the polarity at the input side is point A is negative and point B is positive, and the point B is positive and point A is negative. So after omega t equal to pi, we triggered SCRs T3 and T4, T3 and T4, and it will conduct, and the load current will flow like this, and through the T4, and it goes to A and back to the source, as we know that the point A is negative. So we are getting the output voltage like this, and omega t equal to pi plus theta 1, we are triggering the SCRs S3 and S4, and the SCRs T3 and T4 are force commutated. So at omega t equal to pi plus theta 1, S3 is turned on, and the current flows through the load like this, and S4 is turned on and goes through like this and to the source like this. So this is the path for the output current, and we are getting the output voltage like this, and so on up to the omega t equal to 2 pi. Both the SCRs T3 and T4 from the positive group, and the SCRs S3 and S4 from the negative group will turn on and off alternatively up to omega t equal to 2 pi, and we are getting the output voltage like this. And again, the frequency of the output signal is 6 times the frequency of the input signal. So this was the operation of the single phase to single phase step up cycloconverter by using braid type topology. Thank you very much for your patience.